My dear students, welcome to module 2. So far we have discussed in the module 1 the characteristics of the fluid, and we have discussed the so many properties, then hydrostatic law, manometer principle. Now we are today starting module 2. The module 2 consists of the two portion. One is the hydrostatic forces on surfaces, that could be a flat surface, that could be a inclined surface, or that could be a curved surface, right. At the same time, the module 2 consists of 2b, fundamentals of fluid flow, which is called kinematics. It is a mass independent relation. We will be talking about the velocity, acceleration, displacement, etc. The learning outcome of this module, the student will learn to determine hydrostatic force on submerged plane and curved surface and its application to gravity dam and log gates. You will be able to determine hydrostatic force on submerged plane and curved surface and its application to gravity dam and log gates. I will come to you later. The second objective is the principle of kinematics and hydrodynamics for practical application. We will be learning the basic conservation law. We will be learning how to calculate the velocity, acceleration. We will be also learning the streamline, streak line, path line, types of flow. Means we will be moving in the moving flow system. So that's another objective which this module contains. The sequence of today's lecture will go like this. We have a basic equation of hydrostatic pressure, hydrostatic force and its location for vertical and horizontal surface, hydrostatic force and its location for inclined surface, hydrostatic force and its location for curved surface, problems on above. So this is our today's theoretical portion which we would like to cover. To start with, I will show you a small example of a feeder canal gate. You can see in the animation it is lifting and the water is going. Okay. At the same time, you can see here a big gate wall for spillway control, and that is also going to be lifted in the same way the animation is shown. So these applications are very much important, because we should know if our water is up to this much, what force you need to lift it. You can see in the photograph also very clearly how much force you need to lift this radial gate about this pivot. Okay. So this could be a plane surface. For example, it could be a rectangular gate. I need to slide vertically like this. I can show you like this. It may be a rectangular gate. I will lift it like this and the water will gush into system. It could be a curved system. It could be a curved system like maybe this paperweight. You can see it is a curved portion. Again I can lift it like this. So these are the few examples. We would like to see how to calculate the force for this, what will be the hydrostatic pressure, what is the weight of this gate is going to play a role, etc. Before I continue, I would like to show a small animation of a gravity dam. You may be thinking, what is this gravity dam? The gravity dam is defined by virtue of its weight. It is going to resist the hydrostatic pressure. For example, if this is the gravity dam and water is here, so this water is trying to push this gate and it is going to destabilize like this, correct? It is a gravity dam exactly like this, and I am going to shift it. So it is going to push it. You can see in the animation water pressure is there, but its weight is mainly responsible to make it into the position. But at the same time, you can see if I am tilting, there is a uplift pressure also. So the uplift pressure is reducing the effective weight. So these are the important things we need to consider when we design a gravity dam. What is the hydrostatic force, what is its own weight, and what is the uplift pressure. Apart from this, there could be a earthquake pressure also. Okay. So we will see to it later, but this animation very clearly shows the importance of the water pressure which is in the horizontal direction, the weight of the dam in the vertical direction downwards and the uplift pressure in the upward direction. So higher the uplift, it is not good for the dam. Higher the weight, it is good for the dam, and higher the hydrostatic pressure, it is also not good for the stability of the gravity dam. We will discuss this later. Now, before I continue on the further, we would like to learn. Earlier we learned how the hydrostatic pressure was varying starting from the top 0 to a triangular way. You remember? Now, suppose if I see a compound wall in the plan, I repeat, suppose this is the compound wall. This is the compound wall I am seeing in the plan. So you can see in the cursor, it is the plan. So this portion you are seeing on the top. Definitely compound wall is erected above the ground. So it has got a air pressure on this side and air pressure on this side. So it is balancing each other, it is stable. Is it okay? Now we would like to know how the force will be there, horizontal force will be there to a liquid. Now I am not talking about the vertical force which I discussed earlier also, like this. On the top it is 0 maximum, but I said if it is like this, then what is the force here? Same head. What is the force here? Same head. What is the force here? Same head. What is the same head? P is equal to gamma h. So on this particular plate which is shown to you as an example, it is a horizontal plate. Everywhere the depth of water is same. So this is gamma h, this is also gamma h, this is also gamma h. What is gamma? Specific weight of the liquid. What is the h? It is the height of the liquid. So everywhere pressure is same. Everywhere you will see it's a hydrostatic pressure, everywhere same. If you want to show me this way, if it is vertical, no doubt it is 0 here, maximum here. It is varying with a triangle, exactly like this, you know very well. The moment it becomes horizontal, it's like this. Everywhere same height, you are going to get the same pressure. Is it okay? So we are very clear that what is the kind of pressure this horizontal surface or the plate is going to experience when it is under the water, right? The concept is P is constant along the horizontal surface because head is same everywhere, 1 meter, 1 meter, 1 meter, throughout 1 meter. Hope you understand. Now the intensity of pressure is given by gamma h, which is density of the liquid, acceleration due to gravity into the height of the liquid, plus P atmosphere. What is this atmospheric pressure? This is the atmospheric pressure on the top of the surface, which is going to give you the absolute pressure. So if you ask me what is the fluid force on a plane surface in a horizontal position, so your answer should be everywhere it is same. I will show you one more slide. You can see the same thing. Hydrostatic force on a plane surface. This is a plate exactly like this plate I am showing you. Same plate. Here this portion you are seeing in this diagram with a arrow, correct? And this is the height which is shown here, h, 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 everywhere h. So this is the horizontal surface. So what is the force? I would like to know. The intensity of pressure on this small p into this area of the plate will give me the answer. Again repeat, earlier no, we were only interested to know the intensity of pressure, differential pressure. What is the pressure? Pascal. You know very well, 1 Newton per meter square. But now I want to know what is the total force acting on this plate, if it is under water, if it is under mercury, or if it is under oil, or if it is under gas. Definitely I would like to know the force. What is the force? It will be the pressure into the area of this plate. What is this plate area? Length into breadth. If it is a rectangle, suppose if it is a triangle, half base into height, right? And if it is a circular, pi r square. If it is a semicircle, pi r square by 2. If it is a quarter circle, pi r square by 4. So definitely now we are going one step ahead of that. I would like to know what is the total force acting on a submerged horizontal plate, on a vertical plate, on a inclined plate, all those things, and on the curved surface also. We will come to that later. First read out this statement of the slide. You can see very clearly pressure has been defined as a force divided by the area on which it acts, correct? For fluid at rest, the force always acts at right angles, exactly like this. The horizontal plane surface submerged in a liquid, the pressure intensity small p will be equal at all points, as I mentioned, gamma h everywhere. This leads to the conclusion that the resultant force on a horizontal surface due to that pressure can be computed from the simple product of pressure times the area. It means wherever you go, intensity of pressure is same, here also, here also, here also, as I showed, here, everywhere it is same. So if you multiply the plate area which I was showing you, you get the total force. Okay. So one curiosity of ours, that okay sir, intensity of pressure I know on a horizontal plane is same everywhere, no issue at all. What is the force acting on that? It is going to be the area of this particular plate, maybe this plate, into the intensity of pressure, you get the answer, right. Now question is where this force will act, that is also equally important. If I take the force in a form of a rectangle exactly like this plate, you will say okay sir, intensity of pressure into this plate area, I get the total force. Where it will act? It will act at the centroid of this, in the horizontal position. That particular point where the whole force is assumed to be acting, I repeat, that particular point where the whole force is assumed to be acting is called center of pressure, or Cp. Okay. So you understood one thing, the whole force P is equal to, or F is equal to intensity of pressure into this plate area L into B, and this will be acting exactly at the center of this, which is going to be the center of pressure. Is it okay? So I have introduced you two things now so far. One is the total force F, and next point is where this F is acting. It is acting at the centroid of that particular plate, which is nothing but the center of pressure. Is it okay? So we would like to know this for many combinations, we will see to it. Let us continue the same discussion, again same thing which I have showed you as a diagram, total pressure acting on an immersed plane horizontal surface. You may be thinking what I am talking. This is the water level here, and this is the plate level here. This is my hand is a plate. Okay, this is the water level. Suppose if the pressure here less, more, correct. Now you can see in the slide a horizontal sheet is shown to you of length L and width B. So definitely area is L into B, correct. At the same time you can see the intensity of pressure at that level will be same. So P will be equal to P into A, gamma F into HC. There is a one more term called HC. This is the depth of the center of pressure. HC is known as depth of the center of pressure from the free water surface. HC is called depth of the center of pressure from the free water surface. Example, this is a plate and say this is the water level. So this will be the H is equal to HC. This is the center of pressure at this point C, which I have shown by a chalk. So Cp is here. So this is actually you are seeing this part. This is L and this is B. So L into B, okay, and you can see gamma of the water 1000 into 9.81 into HC. So if you ask me, the formula for total pressure will be P will be equal to gamma into A into HC bar. I will write it like this. Gamma W is the specific weight of the water, A is the area of the plate in the horizontal projection, and HC is the depth of water from the free surface of the center of pressure. Again repeat, gamma W is the specific weight of the liquid or water, A is the area of the plate in the horizontal projection, and HC bar is the depth of water, depth of center of pressure from the free surface. So HC bar represents depth of from free water surface, right. So this is what we have to remember as far as the horizontal position is concerned. We will take the next slide. Free or the horizontal surface of water, you can see here a horizontal free surface upon which the pressure is constant everywhere. Free surface of water in a vessel may be subjected to atmospheric pressure, any other pressure that is exerted in the vessel may be a closed content. The difference in pressure between any 2 points, say A and B, is always equal to the product of the specific weight of water and the difference in elevation between the 2 points. Okay. So if I take the 2 points and I would like to know what is the difference, it will be equal to gamma W into H, that is the intensity of pressure. If the 2 points are on the same elevation, A will tend to B, it will be the same. So there will not be any difference. In that case, PB minus PA will be equal to 0, correct. Let us see one more thing. The total pressure acting on an immersed plane, vertical surface. Now this is very important. This we encounter in most of the dam, in the canal gates, everywhere. So we need to know now what is exactly this. For example, I told you initially a compound wall, you remember, a compound wall on the left side, vertical surface exposed to air. You can see it is the same force acting on the compound wall which is there, correct. On the right side, if you see, you have a vertical plane which is of this form, right. It is a water level, but your plate is starting from here. So it has got some value here, gamma H1, gamma H2, okay. And this particular gate, it could be a rectangular gate, it could be a triangular gate, okay. You may be thinking, you may not able to visualize, I will show you exactly. You can assume that this particular rectangular gate is under water and depth, water level is here, correct. So what you are seeing is this portion which is available in this part of it. You can see near the P value, this part you are seeing, okay. Maximum pressure is here and minimum pressure is here, but water level is here, mind it well, it is under the water, okay. So what is the area you are getting here? In the force P is acting on this particular, say it's like this only, it is a rectangular area. So I would like to know what is the force on this particular gate under the submerged condition. So the value will be same formula, P is equal to gamma W A into HC bar. What is the HC bar? HC bar is the center of pressure. You can see here, mentioned here, centroid is here, center of pressure is slightly below. So this value, if you measure from this point to H bar, this become HC, correct. Area of the plate L into B, you know very well, and this liquid is gamma W or gamma liquid. So that is nothing but rho into G. So that is going to cost us like this. So we are going to estimate on a vertical gate like this, which is totally different than the horizontal gate. Horizontal case, everywhere it was same. So force was acting at the center and center of pressure C and CP both were coinciding in the horizontal case, but the moment I lift it to vertical, you can see the point C is shifted to CP. So center of pressure is slightly below the centroid of the gate. Gate can be anything, it can be a rectangle, it can be a triangle, triangle you know H by 3. If it is a circular, center of the circle, semicircular 4R by 3 pi, like that it will vary from shape to shape. So now we will learn more about the vertical gate. The pressure prism diagram also is shown. Can you see here? It is minimum here, it is maximum here. It is quite possible that sometimes the gate and the level is tallying exactly like this diagram. This red diagram which you are seeing, no? Exactly like this. So it is tallying with the same. Water level is also here, gate is also here. I would like to know what is the force I need to lift it. Mind it well, in that case, central of the figure is here and center of pressure is slightly below, slightly, not much, but it will be slightly down always. Now we will see how to calculate the total pressure P and center of pressure P. Again the same concept, the total pressure P, it is defined as the resultant force exerted by static fluid on a surface. This is the plane surface and this is the force P. I told you, no, that is the area of the pressure prism into the perpendicular length. I repeat again, area of the pressure prism, like this, no, I told, no, like this. So area of the pressure prism into the length, actually it is nothing but the volume of the pressure prism. It is nothing but the volume of the pressure prism. So that will be nothing. We have to calculate P is equal to force intensity of pressure into A. In that case, we would like to see where is the center of pressure. Center of pressure is the point where the total pressure P is acting. Center of pressure is the point where total force or the hydrostatic force is acting. It means if this is a vertical plane, as I was showing you through a plate, this is the force. So it will not act as a centroid, it will be slightly below that. So that value we can obtain by taking the point of application Yc into P and Yp into D. This is the first moment of the pressure diagram and this is in the x direction. So we can estimate those things, but before that we would like to talk about a very important concept, centroid. You have just seen, I have shown you a rectangle. What is the centroid? It is the B by 2 and the A by 2, which is both are same. Exactly, I showed you here also, same thing. Total length 20, say 30, this is 15. Total length 20, this is 10, right? So centroid of a rectangle is here. Similarly, if you take a circular section, maybe circular, you can see the centroid will be the center of the circle. Centroid will be center of the circle. Suppose if I take a semicircular, in that case it will be r on x axis and y it is 4r by 3 pi, where r stands for radius of the circle. Semicircle 4r by 3 pi. I think you might have studied this in elements of civil engineering, correct? I am just reminding you again. Quarter of a circle, mind it well, both the side, x side and y side, both will be 4r by 3 pi. 4r by 3 pi, where r is the radius and pi is 22 by 7. Is it okay? Suppose if I can take a triangle, definitely it will be h by 3 as far as the height is concerned, but as far as the x is concerned, it is b plus d by 3. So mind it well, it is very important, we need to calculate the centroid of the plane figure. Centroid can be a rectangle, it could be a circular shape, it could be a semicircular, it could be a quarter circle or a triangle. So we need to remember this formula because we need to know what is the value of centroid for each shape, right? One more important point, along with the centroid, we normally say centroid is the first moment of area, right? There is one more thing which is moment of inertia. Moment of inertia is the second moment of the area. I think you remember, for a rectangle it is BD cube by 12. I have written here BA cube by 12. You can see here centroid, it is like this, B into A cube by 12, it is along the x axis. For a circular it is pi r 4 by 4. Some people say pi d 4 by 64, both are same, there is no issue, but the moment of inertia of a circle is pi d 4 by 64 or pi r 4 by 64. Area you know very well, pi r square. If you take a semicircle, the area is no doubt pi r square by 2, but the moment of inertia is 0.11 r to power 4. This you have to remember. For a semicircle, the moment of inertia along the x axis like this, it is 0.11 r to power 4. But suppose if it is for a quarter circle, it will be half of this. Can you divide this by 2? 0.11 divided by 2 is 0.055 r to power 4. And for a triangle, it is always bh cube by 36 or ba cube by 36, as I mentioned here, okay? And area remains the same, area is half base into height, same, ab by 2. So mind it well, we need to remember the centroid of a rectangle, b by 2 d by 2, circle center, semicircle r and 4r by 3 pi, quarter of a circle 4r by 3 pi, 4r by 3 pi. For a triangle, h by 3 or height by 3 and b plus d by 3. And moment of inertia for a rectangle, ba cube by 12. For a circle, pi r 4 by 4 or pi d 4 by 64. For semicircle, 0.11 r to power 4, and for a quarter circle 0.055 r to power 4, and for a triangle bh cube by 36. So, these are the values or these are the formulas you should remember. We are going to use this standard formula in our numericals. So, hopefully you understood. In today's concept, today's talk, we are talking about the total force, we are talking about the center of pressure where it is going to act, and we are talking about the different shapes how it is going to be. At the same time, we have understood a formula. The total force is given by gamma w or gamma liquid, specific weight of the water or specific weight of the liquid, multiplied by the area of the plate or the area of the immersed plate into the depth of the center of pressure, depth of the center of pressure from free water surface, depth of the center of pressure from the free water surface. So, all those things are very important to estimate the force which we need to lift a submerged gate. Is it okay? Let us take next one. Now, so far I have talked about the hydrostatic force on a horizontal system, like this C and Cp coincides. In a vertical system, it is going to be like this. You can see here exactly. Centroid is here, center of pressure will be slightly below. Name is C for centroid and Cp for center of pressure, exactly like this. But one question arises, suppose instead of horizontal or vertical, if it is inclined at some angle, I repeat, instead of horizontal or vertical, suppose it is inclined at some angle, say theta, you can see in the slide also theta, what will happen? In that case, definitely it will not be at C, it will be somewhere between C and Cp of vertical position, correct? Example, if C is say 10 centimeter for a vertical, Cp is say 12 centimeter, I am just giving example, do not mistake. For a vertical plate like this, the centroid is at 10 centimeter from the water level, you can see water level 10 centimeter, center of pressure is at 12 centimeter, it means 2 centimeter below the centroid. When I make it incline at any angle, say 30 degree, 60 degree, 45 degree, 10 degree, it will lie between C and Cp. It means it will lie between 10 centimeter to 12 centimeter. So, answer will be between 10 to 12 only, right. Then how it depends on the angle theta, how it depends on the moment of inertia along this line, those things we would like to see. Is it okay? Is it clear? What exactly I am trying to give? I am trying to get a general formula. When theta is 0, it is going to be horizontal, correct? When theta is 90, it becomes a vertical, and suppose if theta is 60 degree, it is a incline. So, we would like to now derive a general formula for center of pressure. As far as the force is concerned, it is the same value, P is equal to gamma W A into Hc bar, that is permanent. But as far as the center of pressure is concerned, I would like to know where is the location, this location for an inclined plate. There is a formula, we will derive it now. So, is it okay? So, now let us read the statement. The area AB of the back face of a dam inclines at an angle theta. You can see here the angle theta, which will vary between 0 to 90. X axis lies on the line at which water free surface intersects. You can see here, if I take this plate exactly like this one, it is going to intersect the water level, that value is here, this point. So, this is going to be your y axis and x axis will be opposite. You may be thinking why I have put different view. Mind it well, this particular plate which you are seeing, this portion, right, this axis will be x axis, this is your x axis and this is your y axis. Why y axis like this? Because it becomes vertical, see it is now theta, it becomes vertical, it becomes depth, that is the reason along this we have taken y axis. Is it okay? Is it okay? Right. Now, after explaining this concept, y axis running down the direction of the dam surface, so that when this becomes a vertical, y remains like this, which is the depth of flow or which is the h, you can say, right. X axis is perpendicular to that, you can see here. You can see A is the area, they have put an arbitrary area here, This area you know very well, it could be a rectangular plate like this, or it could be a circular, it could be a hollow circle, or it could be a triangle, or it could be any other shape, right. So, let us see how it goes. The back area of the AB surface is inclined with angle theta. This is the gate exactly. We are seeing in many industries, they have an inclined face of a concrete in which a metal gate is there, and that we need to lift. We would like to know where it can be lifted. So, x axis lies on the line and y axis running in the direction of the dam surface. Now, center of pressure. Now, entire system is like this. This particular point which I am putting my hand, I will show by cursor, it is here. Can you see that? So, some depth is there. So, it is having some gamma h, gamma h1. Here some more depth is there. So, definitely the pressure will be somewhere like this. That is the thing. You can see the formula is same. Resultant is again normal to the surface. As I mentioned earlier also classes, the hydrostatic force will be normal to the surface. If it is a vertical surface, pressure will be like this. If it is a horizontal surface, it will be like this. If it is an inclined surface, it will be in this case 90 degree, correct, which is the this portion you can see. So, what is this angle my dear? It is a 90 degree. So, if you calculate based on the formula Fr is equal to Pc into A, you get Y pressure or Hp is equal to Hc plus Ixx, moment of inertia along the x axis, which is nothing but along this axis, okay, along this axis, moment of inertia along this axis, right. This is the formula Ixx into Yc, which is the center of centroid depth, into A is the area of the plate which is here, and we are going to get that angle as a sine square theta in the problem. Now, you can see I have the derivation. We have taken a small strip, y sin theta is there, the derivation is continuing, the force concept is same which I defined here, P is equal to gamma Hc bar into A, then this y bar is equal to the centroid which we are going to get directly. So, the total hydrostatic pressure force on any submerged plane surface is equal to the product of the surface area, which is nothing but this gentleman, and the pressure acting centroid of the plane surface, okay, into gamma w. So, those things you take care, you can see the center of pressure general formula has come. The general formula Hcp is equal to h bar. H bar is the depth of the centroid from the free surface. I repeat, h bar is the depth of the free surface from the free surface. I will show you in this diagram also. This sheet you can see centroid is here, b by 2, l by 2. So, Hc will be this value from the free surface. This is the water level here, okay, and I am going to calculate Hc. What is this my dear friend? It is Hcp. So, you can see Hcp is always more than Hc slightly by an amount Ig sin square theta into h bar. It is the along this axis we are going to take moment of inertia, x axis along the depth you can say parallel to the this one line inclined surface, and A is the area of the plate, this is the area of the plate, and theta is the angle. Theta is the angle, I think you can show you in the slide also. Theta is the angle, this is the angle. So, what is your Hc? Hc is this C. So, this depth from the free surface, and what is Hcp? Hcp is the depth of the center of pressure from the free surface. So, mind it well, it is a very important formula we have derived for a general position. You can see here the case 1 theta is 0 degree. This is theta, no my dear friend, I make it 0. So, you can see here case becomes horizontal, sin theta is 0, Hcp becomes h bar. It means the centroid Hc is become the same center of pressure. So, mind it well, it is a very important question in the competitive examination. When the depth of center of pressure becomes the same as the depth of centroid, your answer should be the plane surface is horizontal. Again the question, when the depth of center of pressure becomes the same, Hcp becomes Hc bar. Answer is the submerged plane surface becomes horizontal. If it is an incline, you know very well angle is coming. So, if the theta becomes 0, Ig sin square 0 is 0. Whatever inertia it may be having, whatever area it may be having, it is not going to affect your Hcp will coincide with Hc for horizontal surface. The moment you have some theta You can see you have to work out the IGF for that particular case. It may be BD cube by 12, it may be pi r4 by 4, it may be BH cube by 36, but depending upon the shape. Suppose you may say, suppose if it is a hollow circle, no problem, pi r4 minus small r4 divided by 4, same thing, same formula is same, or pi d4 64 minus pi d4 64, capital D and minus small d. We will solve the problems on that. Suppose if theta becomes 90, instead of theta becoming 0 or incline some angle, it becomes 90. What will happen, my dear friend? You can see it will be maximum deviation will be in the CP. HCP is equal to h bar plus Ig sin square 90. Sin square 90 is 1. A is the area of that particular shape, maybe rectangle, triangle, whichever I am telling. H bar is the same, the depth of the centroid from the free surface. Okay, HC, I told no HC, that is what. So these are all the three important concepts we need to learn as far as the total pressure acting on immersed plane is concerned, right? Is it okay? Hopefully I have told you. Now after discussing this much, we will be now slightly deviating our course. Suppose, as I showed you, I think I will go to the previous slide for your information. You can see here in the you can see here this particular shape. Can you see the shape? Is it a plane shape? No. Can you see this lifting of the gate? What is the shape, my dear friends? It is a curved shape, exactly like this. It could be a curved shape or it may be like this, some curved shape, right? How to calculate on this? Even this gate also you can see, it is not plane, it is not a vertical gate. See, this is a vertical gate. Okay, if I lift this in a dam, it will be like this directly. I will lift it by a crane system, will pull it. This is a plane surface, right? No problem. Plane surface can be horizontal, it can be inclined, it can be vertical, no issue at all. I can work out with that formula. But if it is a curved surface, then what to do? Question is how to calculate the pressure for a curved surface. You can see in the slide also, this is a curve here, how to calculate the force, right? So now let us discuss that particular part, how to determine the force on a curved surface. My dear friends, in this case, hydrostatic force on a curved surface, if you see, this is a small surface. Can you see? Exactly like my hand. In this case, exactly if you see the diagram, it is like this. Anyway, I cannot hold it properly, but still, this is the water here. So this is the curved surface, exactly. How to calculate for this? It has got two components. You remember when we studied mechanics, the reaction at the hinge, it is inclined. See, roller support perpendicular. So reaction in the hinge is inclined. It has got two components, one the horizontal component and one is the vertical component, correct? Similarly, in the case of a curved surface, it will have two components. One is the horizontal component, which is totally governed by hydrostatic force. Repeat again, one is governed by the hydrostatic force, which is a horizontal force acting like this or maybe acting like this, whatever it is. It means if this is holding water, my palm, so one component will be like this, okay, and other component will be the weight of the water. Other component will be weight of the water. So we need to determine what is the value, how to calculate this FH and FV, two components, right. So I repeat by reading the slide. The hydrostatic force on a curved surface can be best analyzed by resolving the total pressure force on the surface into its horizontal and vertical components. So as I explained to you, there is a FH and there is a FV, right. FV can be positive, sometimes it can be negative, mind it well. Suppose if my hand is like this and water is on this side, I repeat, hand is like this, curved surface, but water is on this side, what will happen? It will be pushing it upwards like this. So there will be a FV and there will be a FH. Definitely the resultant will be changing, that we will see later. One by one let us see. So by resolving the total pressure force or total hydrostatic pressure force on the surface into its horizontal and vertical components. Means we are going to divide it into FH, you can see here, and FV. Now let us come to this particular figure. You can see there is a AB. AB is the portion which is a incline or curved, you can say. This curved surface will be having pressure up to this. I would like to calculate what is the pressure present from this point to this point, because that only is going to affect my horizontal force. Indirectly what I am trying to say, suppose if this is a curved surface, you can see, no, it is a curved surface, I will project this particular, this point to this point in the form of a plate, exactly plate I was showing you, no, same, in the form of a plate, and I will work out what is the horizontal force. I repeat, I am not bothered what is the shape of this. I will take highest point of submergence, and this point I will project a line exactly like this. This could be curved, there is no issue, but I will take this portion. It is exactly like this. This point is touching here, right, and this point is touching here. I will take a projection and I will treat it as a rectangle. I repeat, this is very important to understand. Whatever may be the shape, I repeat, you can see here, this is the top point. Top point, I put a projection here, point 1, say point, I can say A. This point is bottom point, I am projecting here B. No doubt, it is having a curved surface. You may be thinking like this. I will take one point here and one point here, exactly like of my chalk length. A point and B point, I treat it as a rectangle. Okay, that force I am going to estimate for FH. Is it okay? I repeat again, this is very important. It is a curved surface, exactly like my hand. Okay, this is the highest point. I will take the point A here, as it is shown in the, let me change my hand. Okay, it is exactly point A here, like here. This is the point A, and you can see in the cursor, this is the point A. Is it okay? This point, and this point is B. In the bottom, this point is B. I will take a vertical projection. You can see it is in the vertical direction from this point to this point, B and A dash. Now, this one I will take perpendicular as a rectangle and work out. That is actually the hydrostatic horizontal force on a curved surface, right. So, one part is clear to you. We are going to make the horizontal projection of the curved surface on a plane form and calculate the horizontal force in the same formula. What is the formula? Gamma W A into AHC. What is the formula for FH? I can say this is FH is equal to gamma W A into HC bar, same way. So, whatever we have practiced for the plane surface earlier, horizontal, inclined and vertical, we follow the same concept with a projection theory. The projection is rectangle, mind it well, it could be of any shape of this shape, no issue. We are going to take the first point here, next point here, make it a vertical like this and take the length along that. That could be a 1 meter, it could be a 2 meter, they will give in the exam. You can see this particular diagram, if you see length, if you want I will just show you same thing. 1 minute, here you can see I will take, suppose it is closed, I will take top point here and bottom point here, and this is the width. It means what I am showing you is this portion, what I am showing you is this portion, vertical portion, right, and the width is width of the gate which is available in the system, that same system. Is it okay? Now, okay, we have discussed about the horizontal component. I think you understood the concept. We are going to have a projected area in the form of a vertical plane of whatever width is there. You have seen the width of the gate, no? Same thing. Gamma A into HC bar, same concept we will apply and calculate FH. Is it okay? Now comes the vertical component. What is the vertical component? The vertical component is the weight of water over the gate. I repeat, weight of the water over the gate. Let us see this portion. You can see I have divided that particular gate with a arrow. For example, you can take my hand only. So, if this is water, whatever weight is there up to say this is the top. So, what is the weight of the water, this much portion, that I am going to take as FV. Okay, this is going to represent my FV like this, right. So you can see it is divided in now it is coming. See, you can see here this weight I want A, B, A dash, C, D, A, this much portion, whatever the weight is there. Then you may be thinking, what is this, sir? We should know how to calculate weight. Weight is nothing but the volume. Volume is nothing but the area into length into gamma W. So we are going to calculate the weight based on volume into gamma W. Volume is nothing but A into L into gamma W. That is very important. Weight we are going to calculate. For example, for the first case, it is a rectangle. I think you are very smart to calculate the rectangular length and width, A by B, whatever the length is there, say length is 1 meter perpendicular to the board, right, that is going to be 1 meter. So area into 1 into gamma W 9810, that is the weight of this particular thing acting at the center. But this particular portion depends on the shape. It may be semicircular, it may be cylindrical, or it may be quarter of a circle, it may be half of a circle. Those things we will calculate based on the particular shape. If it is a semicircle, I will take pi r square by 2. If it is a quarter circle, I will take pi r square by 4 is the area into length. Length of the gate will be given perpendicular to the board. Okay, whatever we are seeing is this side. This line is like this. So the length will be exactly perpendicular to your side. Is it okay? Right. So that is what is required. You need to understand how we are going to calculate. Suppose if the water is like this, finding Fx is to determine the force acting on a plane submerged oriented perpendicular to surface. In that case, you can see here I have shown you a very nice way. This is the curved portion. Can you see in the cursor from this point, say 1 to 2. I have projected an area. Can you see? I have projected an area like this. Is it okay? Same thing, exactly like my hand, and you can see here this is the thing. You can see here, right. So this portion is this point, and this portion is this point. So this is the length, and Fx will be acting here accordingly with the formula, same formula, gamma W H into Ax. Ax, why it is saying the subscript? Because we are projecting that curved portion to a equivalent system. That projection is rectangular, as I mentioned very clearly. So mind it well, finding Fx is to determine the force acting on a plane submerged surface oriented perpendicular to the surface. Ax is the projection of the curved surface on the y-z plane. Similar conclusion can be drawn force in y direction also. Is it okay? So this is one part. Then second part is the same which I told you, the weight of water over this portion. You can see this portion is having a rectangle here and a small portion here. So what I will do, I will take volume of this rectangle, I will take volume of this rectangle also, and I subtract this quarter circle. That will give me the answer, correct. So we will, when we solve the problem, you will be knowing how to calculate the x component, how to calculate the y component, so that you will be able to determine the force acting on that. So definitely the horizontal part and the vertical part is the weight part, horizontal part is the projected part. So when we solve more problem on this, we will be able to understand better. So I stop with my today's discussion. I know that it is a bit heavy today, but mind it well, today we have covered what is the force acting on this particular submerged plate under water, which is submerged up to this level. So everywhere pressure is same, center and center of pressure will be same, this we will be acting like this exactly. Then we have understood how it is going to be working on the inclined plate. Center of pressure will be here and centroid will be here. So force will be acting here, right, and when it is inclined, somewhere it will lie between C and Cp. So with that we have obtained a big important formula, which is H center of pressure is equal to Ig sin square theta Ah bar plus Ah bar. So, that is a very important formula in which we can determine the center of pressure position when theta equal to 0 horizontal, theta equal to 90 vertical, and theta is equal to any theta is inclined. And then we discussed about how to estimate the forces on a curved surface. Curved surface has got two component, one is the horizontal and other is the vertical. Horizontal is the projected portion of this calculated on a rectangular basis to calculate the hydrostatic force. The vertical portion will be the effective weight of the system. So, with this I stop. Hope you will be joining me tomorrow for the problems on the system. Thank you.